Thank you. Well, it's a really pleasure to give a talk to this audience. Thank you again for inviting me. So today I'd like to tell you about one of the projects we have in my laboratory at Stanford. This particular topic will be kind of a out there discussion of how one might be able to create an associative memory in this new system that we call confocal cavity QED, and how it might do some beneficial things, recall and enhanced recall and storage capacity. The folks who have really done most of the work on this project, or the folk, is Brendan Marsh here. He does both experiment theory in my group, of course with the aid of many other students in my group, some of which are shown here. And then also we have the generous theory support and discussions with several folks, including Jonathan Keeling at St. Andrews, Surya Gopal Christian, who's in the audience, and Surya Ganguly, who's at Stanford. So before I begin, I just want to give some caveats to set some expectations. So what I'm presenting here is not a device. It's not a disk device. It's not something that, is an architecture that I think is very scalable. But it's more a test bed, a platform to benchmark and explore some ideas in driven-dissipative computing that might be interesting and might eventually one day lead to something a little bit more scalable. So in this talk, I'll present mostly semiclassical results, not fully quantum results, although the system can behave in that manner. And at the end, I'll present some more fully quantum intuition for the system. So in this audience, I probably don't need to remark that a neural network can be viewed, certain types of neural networks can be viewed as spin glasses. But for those of you for whom this is new, one can think about it just a normal spin glass, which is a Ising model with some randomly signed Jij, as representing this kind of circuit model and vice versa. And that has long been recognized, even before this, but more thoroughly in this paper, that these kinds of systems can allow access to solving important and hard problems from a wide variety of applications in fundamental science and technology. So what I'll be talking about is kind of addressing this spin glass-like system, but kind of in an unusual form, not something where you grow the material and then you cool it down and you study it, but rather that you have a driven-dissipative system that nevertheless has a frustrated character. And so that system, like so, can be coupled to an environment, and maybe you can engineer that coupling in a beneficial way. And maybe you can drive the system. So you drive it out of equilibrium and you ask what are steady state dynamics. So the dynamics for this kind of system is no longer unitary. It usually, you have the unitary bit, but you also have this dissipative bit, which often can be described with something like a Lindblad term in this master equation. So the general idea, and I want to emphasize, it's not sure, no one's sure whether this is an effective approach, or at least I'm not sure. But it's interesting to ask the question of whether instead of coming down in energy in an equilibrium system through many local minima to try to find some optimal ground states, one pushes this out of equilibrium, represents this energy landscape as like a gain landscape or some other cost functional landscape, and pumps the system from some vacuum state upwards until the system reaches some equilibrium of gain and loss, if you think about this like a laser, and the system oscillates or condenses or lases in a particular state first. Okay, that's kind of too good to be true to say that it'll always happen the first one, because these other states can be very, very close. But the hope is that it gets to a good enough state more readily than having to explore an extensive number of local minima on the way to this state. So again, it's not sure if this approach works, but it's worth exploring experimentally, I believe. So a good excuse for exploring this experimentally is the associative memory problem. Generally, associative memory problems are kind of more easy instances of an NP-hard problem. So it's a good place to start, just to cut your teeth. And so the idea behind associative memory is that, if you think about memory in a biological system, you can store many different memories, and if you encounter something that's similar to that memory sometime in the future, you can recall or pattern complete memory. So if you have some memories C mu, some list of them, and you store them, and then you're encountered later on with some corrupted version of them, then the associative memory can recall them with some high fidelity, even if it's not a very good pattern to begin with. So this kind of model for associative memory can be made into a statistical mechanics formulation. This was done by John Hopfield in the 80s. That looks like this. It looks kind of like what you would expect something to go into an Ising model with a JIJ. It's given by this what's called a Hebbian learning term, where you just create the JIJ through the outer product of these patterns, so suitably normalized. So that's a very particular choice and has some very interesting properties. So if you analyze the spin glass, like Hamiltonian for this, you can paint an energy landscape that has many local minima. This is not in the glassy phase necessarily, where the minima are kind of very, very narrow with very steep mountainsides, but they have large basins of attraction, where if you're kind of close, you start with some pattern here, like with the greatest atom ever, dysprosium, and you kind of move away, then the distortion may not go to a different minima. It will come back with some high probability. So that's the idea behind the good recovery of high fidelity recovery of associative memory. And it was proved long ago that such a system can have an extensive memory capacity given by about 0.14 times the number of spins in the system, and before it becomes too glassy to allow recall. By glassy, I mean these, in a hand-wavy sense, these basins become too narrow and spiky. So the question that I want to pose is, can we do better than this by moving this whole system out of equilibrium and driving it? So a great system for exploring that kind of driven-dissipative system is cavity QED, because it allows you to have very strong interactions between the spins and the thing that is kind of mediating interactions among the spins, in this case, photons. So this is a cartoon of the general system that I'll be talking about. It has two mirrors. It's a Fabry-Perot cavity with high reflectivity. That Fabry-Perot cavity can support electromagnetic modes between them. That kind of looks blue here. What's different than most cavities, that instead of just one mode, like a Gaussian TM00, I'll be talking about a multi-mode cavity, in particular confocal cavity, where many synthetic modes can arise all at once that have local kind of compact mode volumes, like so. And each one of those can form at the position of a BC, or small clump of ultra-cold atoms, that's shown in red here, at positions, say, Ri and Rj, that are held in place, in a particular place, by these green laser beams, which are meant to represent what we now call optical tweezers, some other laser beams that can hold them in position. And then what's really nice about the system is that as you're pumping it, adding photons into the system by scattering, Rayleigh scattering, coherently scattering photons from this pump off of these atoms to populate the initially vacuum state of the cavity, that light that does start to leak out can be imaged on this camera and beat against the local oscillator of the pump to form a hologram, or a spatial heterodyne, that allows one to pick off the spin state and where it is as a function of time. So just to reiterate, the positions of the atoms, where you place them deterministically with your tweezer array, defines the problem. I'll show why in a moment, the JIJ. The driven-dissipative system, it may or may not, we think so, provides some natural error dissipation, in the sense that if the spins are configured not optimally, then the system has a little less gain, and that kind of, the light that's generated from that will leak out more readily and dissipate, while new light, new coherence gets pumped into the system to restart. The strong atom-light interactions means that there is a possibility, maybe only transiently, for entanglement to develop among the spin sites, and that entanglement, that correlation, may be a resource for trying to find that optimal state, and we can investigate that. And then there's this phase transition that happens as you pump harder and harder. The spins organize. It's not a lasing transition. You're starting with a coherent pump. It's what's called a super-radiant transition. And the correlations that develop in the second-order transition may also help. We don't know. That's something that can be investigated. So these are the questions we want to explore. Is there a memory capacity that's greater than a Hopfield network, and so forth? And that's what we've addressed most recently, and what I will tell you about. So this is the mess that it is in the laboratory. It's a spaghetti of cables. You've seen many pictures like this. It's similar. We can create a BEC every 15 seconds with 10 to the 5 or an ultra cold gas with 10 to the 7 spins. That's our resource for making a network. And the photons, the light interaction is provided by this special kind of cavity. It's not a single mode cavity, it's a confocal cavity. It's created by carefully engineering the space between the mirrors that can be controlled in situ. So for the aficionados in the audience, the single atom to single mode coupling is about 1.5 megahertz. That's what's called G0. If you form this ratio of the coherent coupling squared to two dissipative mechanisms, light leaking out of the cavity at a rate kappa and spontaneous emission gamma, you get what's known as cooperativity. And if that's greater than 1, then you can start to generate systems with non-trivial quantum state fidelity. In our system, it's about 5. But this is actually not the cooperativity for our system, actually. Because it's a multi-mode system, we get to coherently superimpose all the electric fields for the modes that are supported at the same time. And they constructively interfere to give you an electric field spike that greatly enhances this by a factor of almost 16 to something that we've recently measured surpasses 80. And that number, cooperativity of 80, is state-of-the-art and allows us to at least hope that there could be some quantum effects going on. So let me dig a little deeper into this new regime of cavity QED called confocal cavity QED. So this cavity here, which I just sketched, has a geometry such that the length of the cavity is equal to the radius of curvature of the mirrors. And so you can kind of see that it forms this kind of pattern with respect to a circle. So the modes in a ray tracing picture look like these bow ties. And so it naturally has some symmetry that gives you simultaneous degeneracy of either the even or the odd modes at one time. So if you just say, let's pick the even modes, family of even modes, and you're just a little bit away from confocality, L is a little bit greater than R, you can start to separate all the different transverse modes. So this is the fundamental Gaussian, this is like the TM02 and 20, et cetera, et cetera. But as you get closer and closer to the degeneracy point, then those modes start to blend together until you get a nice, compact, tight bandwidth of degenerate modes. And we've measured that we get hundreds, almost 1,000 modes degenerate all at the same time. And so that, of course, it's not perfect. There's a little bit of spread that's due to aberrations of the mirror. But if you pump the system red detuned by far enough away, delta C away, then from that perspective, this looks like a tighter and tighter compact mode bandwidth, and looks kind of like an idealized degenerate cavity. So as I mentioned earlier, we can take holograms of the light by interfering the pump. And after processing it to remove aberrations, you get these little stripes that then tell you the amplitude and the phase of the light coming out. And so if you have, say, a BEC or a little clump of atoms off to a side, you get the amplitude plus its mirror image because of the symmetry, and then you get this phase profile whose interpretation I'll explain in a moment. But you'll see some pictures like this where we put these together using this electric field and amplitude, phase and amplitude color wheel. So the model for how the system works is given by this energy level diagram. We happen to use rubidium-87 for ease. And the essential point of how we get this to look like a spin model is that we use a double Raman pumping scheme. So the cavity light is at the same frequency. It's given by the coupling G of I of M, where I is the ith atom, M is the mth synthetic mode. And then there are two pump laser beams superimposed, one at a smaller frequency than the other one, which then completes this kind of bow tie Raman pumping scheme with these hyperfine levels to give you effective two-level system. So as I mentioned earlier, we can write down a Lindblad-Master equation to describe this. What the unitary dynamics look like is given by a multimode extension of the well-known Dickey model, which has a sum over the energies of the NM synthetic modes, the spins of the atoms here, and then the interaction term between the light and the spins with an envelope given by the mode shape of the particular photonic mode that this spin is coupled to. And there's a sum over that, and that sum will be have very interesting consequences for changing the range of the interactions and the sign of the interactions. So here, what I'll be talking about in most of this talk is the limit where we have many spins per site. That's to enhance the cooperativity to allow the dynamics to proceed well before any spontaneous emission happens. You don't have to do that. You could, there are ways that we know of to go down to a single spin per site where it's a fully quantum model, and I'll mention that at the end of the talk. But for right now, these are collective spin operators. So if you pump this transverse system harder and harder, then you go from a situation where all the spins are, say, spin down, like so. They're not interacting, you only have vacuum fluctuations in the cavity, to a super radiant phase where you get a burst of light coming out of the cavity, and you get many photons running around the cavity, bouncing back and forth between the mirrors. And in some picture, through virtual exchange of those photons among these spins gives you this interaction where now the spin kind of space is in the from the z to the x-axis, either plus or minus, like so. So, these are the order parameters that happen at this phase transition at a critical coupling strength, GC, which is proportional to the pump strength, like so. Okay, so how do you understand this superposition of these modes, and how does that provide you with interesting GIJ connectivity matrix? Well, one can kind of just picture in your mind that you start out with a lot of these TEM LM modes, where the L and the M are indices that tell you how many nodes you have in the X and the Y direction. And you take a sum over them, a coherent sum over them, maybe hundreds, 1,000 of them. And what you find is that you can get what we call a synthetic mode, which is a very tight wave packet for a photon that's in the superposition. And the width of this is given by kind of the resolution, the effective NA of those cavity mirrors. It's how many modes can be superimposed to give you this tight electric field spike. And this is just kind of a basis transformation. You can tile the interior of your cavity with these little spikes just as well as you can decompose the modes into these Hermite Gaussians. It's a basis transformation, but one that is relevant to the fact that you have little clumps of atoms that are tiny dielectrics that couple to this electric field. So by using this synthetic mode basis, which is more efficient, you have a bright mode and you can ignore the dark modes that do not couple to the atoms, and take in a polaron transformation in this basis, you can write down that multimode Dickey Hamiltonian in this more kind of understandable Hamiltonian that in terms of looking at spin physics. And so you get this spin interaction, and then you get this transverse field here that's just given by omega z, which is some Raman detuning times these operators, which these are displacement operators given by the polaron transform. Displacement operators for the synthetic modes. So the essential point is that you get this now you get this effective coupling JIJ, which is the superposition of a photon being scattered into mode M from atom position Ri into via that same mode, CM, to another spin at Rj. So this is what gives you that connectivity. And it's the properties of this that we'll analyze now to tell you how you can actually use this as a network. So if we kind of go away from the ray tracing picture of a multimode cavity, in particular a confocal cavity, and actually plot what the electric field is, it looks like this in the cavity. And it's instructive to do so because there's a lot more, there's a much richer structure of light going on inside the cavity than just this bow tie would lead you to believe. So again, if you look at the cavity field, you see there's some structure there. And that structure comes from two components that come out of this summation. The first component that comes out of the summation is a local field, a local emission. That's an exponential. It's a Bessel function, but it's kind of exponentially suppressed with some length scale given by the width of that synthetic mode, which is proportional to how many modes are supported by the cavity. This gives you a local interaction. If these two spots are closer than this range, then they can virtually exchange a photon and mediated interaction. The other background here, it's down by about a factor of 10, looks like this. This is what we call a non-local field. It has a Euclidean structure, but a very unusual one. It's not the usual like cosine k delta x. It actually is the dot product of the positions of two particles. And I don't know if maybe you all know, but I've never seen this in any kind of work where any other physical system where you can get an interaction of this form. But it exists in this system, and it's basically because spot here, the confocal cavity kind of is defined as having the property that the object image gets superimposed with the Fourier transform of the object image through a round trip. Okay, so the object and the Fourier transform get superimposed, and a spot looks like a cosine off center, and so that's how you get these cosines here. Another way you look at it is that it's a superposition of a lot of GUI phases. Nevertheless, it's exciting because just by moving the positions of Ri and Rj around, you can change the sign of this. Okay, you can just kind of plug in what you want and you get the sign. And so if you have three clumps, you can arrange them in such a way that you get geometrical frustration, which is the crucial ingredient to having a non-trivial network that realizes a graph that encodes some interesting problem. We've demonstrated this experimentally. We can take some clumps of atoms and move them in position so that the cosines interaction between all of them are all positive, so you get all ferromagnetic. Or you can have where the sign flips and you get some spins that are up and some spins that are down. And of course, 0 and pi, you can reread this as spin down and spin up. And this again just highlights the fact that by looking at the hologram coming out, you can read out the spin state. And so, you know, I don't want to belabor this, but like you can kind of consider the system as an active version of a quantum gas microscope, where instead of just using a high NA optical element to image what's going on inside your quantum system, you can actually reflect those photons back many, many times onto that same system to build up interactions. And so that's the active part. Okay, so what are the connectivity regimes of this particular functional form? So we explored this by kind of numerically, just by kind of randomly positioning clumps of atoms with a different Gaussian distribution width normalized to the intrinsic width of the cavity, which is the TM00 mode, that waist, which is, we call it W naught. And so if most of the clumps are within that W naught, then most of the interactions, this thing is mostly positive, and so you get a ferromagnet, a generalization of a ferromagnet. But if you start to spread out a little bit more, where this can sometimes change sign, so you get this lopsided distribution of Jij, you get some of these blue connectivity points, and you get what we call the associative memory regime, in analogy to that of the hot field model. And if you go too far out, I wouldn't say too far, but if you go, several factors out away from the center of the cavity, then you get more of a 50-50 Jij distribution, and this starts to look increasingly like the Sherrington-Kirkpatrick spin glass, which is a random distribution of pluses and minuses. And so you can paint a phase diagram where there's a transition between the ferromagnetic and this other regime, where this other regime is kind of divided between a crossover of an associative memory, where you have large basins, to something that increasingly looks like a Sherrington-Kirkpatrick spin glass with smaller and smaller basins. But in the middle here, this is, you can call this a new regime or new type of spin glass. And we've been doing parallel tempering Maracalo to understand its replica symmetry breaking properties and so forth. Okay, so setting aside the spin glass aspect, let's ask about what happens to the dynamics of the spins deep into the superradiant phase. So we're going to go through the threshold. We're going to ignore what happens at the threshold. We'll go deep into the ordered phase. This is why I'm calling this more of a semiclassical analysis. And then write down kind of an effective master equation for the coupling to the bath, and ask what does the bath do. And so what you can find out by analyzing the kind of rates of increasing the energy of the system and decreasing the energy of the system as photons leak out of the cavity, you can see that the ratio of gaining or decreasing energy kind of looks like a Boltzmann factor, where small spin flip energy is close to or less than the pump detuning. And so you can define an effective temperature for the system, which is given by delta C, that detuning. So that's kind of a nice effective equilibrium model for what's going on here. So taking that and then asking what happens to the dynamics of the system, we can learn something interesting, which is that if we take the limit of many atoms per clump, so the spins are really kind of all up or all down, okay, and you can write a mean field model for the system, then what we see is that we get something that naturally looks like steepest descent dynamics, which is very different than what you do with the hot field model, or generally like on a computer where you employ Glauber or Metropolis-Hastings-like dynamics to kind of stochastically bring the system down to a ground state. Here, the system deterministically knows which way to go because of the energy bias in flipping the spin with the largest amount of energy that can be taken away from the system. So a typical trajectory of the energy of the system looks like this for a 5-spin network, where the first spin that flips just by pumping the system well above threshold has the largest energy extracted, and then second and third and so forth. And this happens about an order of magnitude in time before spontaneous emission occurs for a system with realistic parameters that we can realize in the laboratory. This is just another kind of way to look at this. You can see that each site's ensemble magnetization flips in a particularly ordered fashion until it stabilizes with some up and some down. And you can verify that that's the right way to do it at the end for optimizing that graph. So what's nice about this is that it naturally implements steepest descent, which is more efficient than doing this using Monte Carlo or like what you would do on your computer. And that's kind of a neat property. It also does something else that's interesting, which is that it allows you to effectively have a larger basin of attraction. So you might think that the basin of attraction is just given by the GIJ matrix and its structure, but you also have to have dynamics involved in order to know how large your basin is. So what we found is that by using steepest descent dynamics, which it naturally realizes, the basin size, how many errors you can correct if you plug in some corrupted image versus the stored image, can increase by a significant amount by using the cavity dynamics versus the dynamics from, say, zero temperature Metropolis-Hastings or Glauber dynamics. And the intuition behind that is simply that these stochastic methods get it wrong when you're up on the valley. When you're at the crest of the mountains, and you can kind of get around which valley to go into, whereas these deterministic steepest descents will actually know each time where to go, and that's more efficient. And so you can calculate, by how much this increases the basins, and you find that you get an exponential scaling of the number of metastable states that have extensive basin sizes that you can utilize for memory. And that's kind of a little bit shocking, because the lore is that spin glasses, can't be used for storing memories because they have, minuscule basins of attraction. But we actually find if you change the dynamics that you use, you can actually increase the basin size in a way that is extensive and encode an exponential number of memories, even in that spin glass regime. So how would you load in? That's not the whole story. If you want to use this, you got to be able to load. So we found that the number of memories that you can load into the system greatly exceeds the limit by the hot field model, which is about 0.14. It can go all the way out to of order n. So that's very exciting. That's because of that enlargement of the basin of attraction and the greater fidelity. And you can use a simple linear mapping scheme using a spatial light modulator to load them up to n. Just by taking what you want and putting it into a form that can be stored. If you want to capitalize on the, so this matches the best known, by the way, for some like non-physical versions of JIJ, but this is a physical version that we can implement. If you want to recover that exponential capacity, you would need a nonlinear mapping scheme, which is more difficult to implement in the laboratory, but it's not impossible. So the last slide I'll present is that allusion to a fully quantum model where we go down to a single spin 1/2 regime. There we can use quantum trajectory simulations to ask how well, as you pump the system up, pump it through the transition, that's this red curve, this is the transition, how do the spins organize under realistic parameters for 8 sites. And what we find is that there's a region where there's significant entanglement among the spins. You can measure it with entanglement entropy or logarithmic negativity in these trajectories. And what we have found, although I don't have a plot for you yet, is that it seems to be that the amount of entanglement is correlated to the probability for success of actually organizing into the correct state, which we can brute force figure out for a network this size. And if we add noise or make it more semiclassical, then we make mistakes more often. So this is a resource. We have some intuition for why that is. We're still working on it, so it's TBD. But that's kind of a hint that if we can go down to the single spin 1/2 regime, this kind of driven-dissipative system would be effective. So let me summarize, and then I'm happy to answer questions. So with confocal cavity QED associative memory, we have this interesting new tunable knob that can allow us to go from ferromagnetic associated memory, correlated spin glass, or Cherenkov-Kilpatrick spin glass regimes just by moving the tweezers around to where the atoms are placed. It seems that the dynamics above threshold realize a natural version of steepest descent dynamics, which is more efficient than Monte Carlo, or at least can be. So it means that the dynamics matter. Steepest descent improves the fidelity of the network with respect to the Hopfield model and the capacity by this amount. And you might be able to get an exponential capacity with nonlinear programming if you're willing to work harder in your optics before the cavity. It's weird that spin glasses also possess extensive bases of attraction. I don't think that has been noted, but we can see that with these particular dynamics. So you can encode memories in a spin glass. And so now we're exploring the transition where it seems like you can actually get some transient entanglement, and that might help with solution finding. At least it seems like that for realistic parameters. Experimentally, we're now playing around with 5 sites. Right now, my students, hopefully, are measuring organization with 5 sites. We hope to be able to extend that to tens of sites soon, and we'll be presenting those results in the coming year or so. So with that, I'd like to conclude and remind you of all the great people that I get to talk to and work with. We also have 2 other results recently that are kind of fun. We've created synthetic phonons in an optical lattice using a similar cavity QED system, and that opens up some interesting doors of quantum simulation with phonons involved. And then we kind of found a weird way to topologically pump one-dimensional dipolar gases into excited states that one may or may not like to call a quantum scar state. And we're now exploring the properties of those scar states by measuring the rapidity distributions, the quasi-particle momenta of those states. Okay, that's it. Thank you.
I guess I'm curious about the intuition about what the quantum effects will do in this memory formulation. Like I would think, for example, tunneling would be bad for memory recall because you could escape the minimum you're supposed to come back down to. Is there some other like quasi-classical way of understanding how the quantum entanglement would help?
Yeah, I mean, like I said, this is still a work in progress, but the intuition is that, if you're organizing from Z down to some states that are X plus minus, entanglement kind of allows you to form the superposition states, allow you to go through the center of this sphere and kind of bypass local minima that you can't if you're semiclassical. So by having that superposition, that correlation allows you to bypass some of the stumbling blocks that the semiclassical spin system cannot.
Hello, thanks for the great talk.
Hi.
I was wondering how much flexibility you have in tuning the interactions for more general quantum simulation applications. So I guess I'm wondering about your input about the range of experimental feasibility for tuning the parameters in the interactions that you already have, so like W0 and also the parameters in the local interaction, and whether or not there'd be any possible modifications you can make to the system to get a different functional form of the interactions.
Okay, thanks, Tama. It's a good question. So I showed you with the double Raman scheme how you can get a ZZ interaction, Ising interaction. With a simple modification, you can get an XY model with the longitudinal transverse fields. In terms of the range, the W naught is set by kind of geometry to about 35 microns. We can push the atom, we can trap the atoms out to hundreds of microns, so you can go anywhere from kind of them all at the center to really an uncorrelated random JIJ matrix. But those are the two, X, Y, and ZZ are the easiest functional forms in this kind of dispersive regime. I hope that answers the question. Okay.
I actually had a related question to that, which is, let's say I restrict myself to the ZIZJ form. Yeah, what in theory are the possible values of like the JIJ matrices that I can program into, like assuming I can control the positions, you know, arbitrarily. Yeah. It's presumably not an arbitrary JIJ matrix that I can program, but like, is there like a nice characterization of what matrices I can?
Okay, you can certainly get a random JIJ with the diagonal being large and mostly the same, but the off-diagonal ones can be more or less random. For like something that's very structured, I think that some things are hard. I don't know if we've explored exactly what the constraints are, but like, you know, what kind of level of symmetry you can have in the off-diagonal elements. I think there's some are possible, but I'm not willing to say that anything is possible.
Okay, thanks.
So you mentioned that there's an exponential amount of memory in the spin glass phase, but those are metastable. So can you actually give me any quote for the time scale for the steepest descent algorithm and then like the stability of this local minimas? Because otherwise, I guess if things are kind of comparable, maybe it's or maybe similar. I guess this exponential capacity of this memory is maybe too fragile to be used.
Okay, yeah, so there's this, so in the Hopfield model, there's this distinction between the associated memory and this kind of metastable regime, and then there's the glass regime. So associated memory regime, every minima is very, very close to the ground state, like it's more or less the ground state. And the kind of, then you get to percolate these kind of metastable states. Those actually, you know, if you're robust to a energy scale of J, like if you can't extract J in any way from your system, then those are going to be fairly long-lived metastable states. This lies within that kind of notion of these metastable states where they're stable unless there's an easy way to remove J. In our experimental system, that's the equilibrium version of this. So in the confocal cavity QED system, everything gets scrambled at a time scale larger than 1 over delta C, or much, you know, some, you know, normalization of that, because the heating from the stochastic leakage of light coming out of the cavity eventually scrambles things. But what we've shown is that there are regimes that are experimentally relevant where the system reaches a steady state before that bad heating regime takes off again. And so, you know, from this non-equilibrium standpoint, there's a Goldilocks regime where you can measure what's happening before the thing heats up to infinite temperature. And yeah, okay, that's not exactly the answer to your question, but I think that would be true even of these metastable states, because they're protected by a spin flip. Are colleagues allowed to ask questions?
Yeah. So thanks for the nice talk. So I have a basic question. So is the picture you had at the beginning, does that suggest that the minima, let's say the minima of the spin model is actually not the ground state of the system? Like there is because you can create that by using the laser. So does that mean that there is an intrinsic like lifetime for that?
Yeah, yeah. So I mean, the ground state of the system is a vacuum state.
And the lifetime is long enough that you don't need to.
I mean, with zero pumping, once you start pumping more photons, then the low, you know, it's a non-equilibrium system. You're driving it, and so you can't really interpret what I showed as a free energy. But if you squint, it kind of looks like a free energy curve. It's more like a gain profile. Like if you think about a simple laser, like it's a gain profile overlaid over different modes. In our case, those modes are spin configurations. There's some gain landscape.
Limit the time, like how long this you can use this as a memory for? Is that the main
so that's what I was,
limitation?
I guess, tangentially trying to answer the other question, which is it doesn't live forever. Like it'll heat up, just constantly. It's unbounded, but there is a little bit of a regime where you get some cooling dynamics from, you pump the system to the red side of this Lorentzian bath. And that the red, the lower energy side of the Lorentzian bath, because of that how that curves down, the red side, you actually get initial cooling dynamics before eventually you get heating dynamics. So there's this like transient regime where you can get cooling. It's somewhat like laser cooling.
Could you expand on what you said about trajectories and whether that's an experimental effort or a theoretical?
It's both. Thanks, Vedika. So right now it's theoretical. So we're just doing trajectory simulations we can do up to 10 sites with a few spins per site, and to gain intuition. And experimentally, I think we know how to take trajectories of the individual spins by doing the spatial heterodyne or hologram as a function of both position and time. It's tricky, but we know how to do it, and that we will be doing that. And then the experimental difficulty is just getting down to the smaller spin regime, and that I think we know how to do as well. So we don't have a theoretical treatment right now to bridge in the middle where our experiments are. If we have many spins per site, then it's just mean field, and you get the steepest descent. Go to one spin or a few spins per site, we can treat with these trajectories, and I think we know what happens. Experimentally, we're in the like mesoscopic, kind of region, like hundreds of spins, thousands of spins. We're looking at cumulant type techniques to figure that out. It's a little tricky, but that's highlights why people like me who are experimentalists need to actually do the experiment. We can't just calculate it at this moment in time.
All right, if there's no more questions, let's thank Ben again, and also
Thank you.
Kristen.